Welcome to the second part of Unit 6. In this part, we're going to introduce types of forces and how we're going to label them throughout the rest of the semester. So first off, there are two types of forces. I guess I should clarify that a little bit because we can divide forces up in a variety of different ways, and in this unit, we're going to divide it up as contact versus non-contact forces. In a later unit, when we talk about work and energy, we will divide forces up in a different manner. Okay, so let's look at our contact forces. Tension is a force that comes from strings or ropes, and because it's a string or a rope or maybe even a chain, really you can only pull with a tension force. A normal force comes from contact between two surfaces and could be either a push or a pull. This is the use of the word normal in the mathematical sense. It is not the use of the word normal like the thing that you normally do. In math, remember that if something is normal, that means it is perpendicular. So by normal here, we're making a comment on the direction that it is perpendicular to the surface of contact. Okay. Example of a normal force would be if you're sitting on a chair, the force between you and the chair would be a normal force. Another example is if you are pushing on a block, then the contact between your hand and the block would be a normal force. Okay. On the other hand, if the block had a handle and you were holding that handle and pulling on the block, the contact force between your hand and the handle would be, again, a normal force. Friction. Friction comes from the contact between two surfaces and points in the opposite direction of the motion. We have a slide coming up where we go into friction in more detail. Okay. All of these require contact. The string has to be touching the thing it's connected to. Normal forces, you have to be touching in order to have them. Friction, again, if the block isn't touching the surface, then there's no friction there. On the other hand, we have forces like gravity. I can take a block or a ball or whatever, and I can let it go in the air, and gravity will pull it downward. Okay. Keep in mind that gravity is another name, or the force of gravity. Gravity has another name, and that other name is weight. Okay. Any two objects that have mass will have a gravitational force between them. In a later unit, we're going to look into the force of gravity in more detail. We also have the electric force, which results from charged objects pushing and pulling on each other, or the magnetic force, where we have a magnetic interaction between two objects like a magnet and a paper clip, or the magnet in your fridge, something like that. You may see electric and magnetic forces in this unit, but not in any detail. Okay. Next semester in Physics 202, we will go into those two forces in more detail. And for inclusivity purposes, I included the last two forces here, the weak force and the strong force. Both of those occur on the atomic level. So the weak force is the force that governs radioactivity, and the strong force is the one that binds atomic nuclei together to keep all those protons from repelling each other. And pretty much this is all you're going to see about those two forces in physics this year. Okay? So I label my forces with a very specific labeling scheme. Okay? for a very specific reason. It helps you keep track of what's going on. Not this unit. This unit focuses on Newton's first and second laws, but next unit we'll be looking at Newton's third law, and having the labels as I do them helps with Newton's third law. So what are my labels? Okay, so for every force, I identify two things: the cause of the force and the thing experiencing the force. The first subscript is the cause. The second subscript is the object that is experiencing it. So when I say it, I have the force by object A, or caused by object A, acting on object B, FAB. Or I could have the force caused by object B acting on object A. Okay, I use capital F for any generic old force that doesn't fall into any of the following four categories. I use capital N to represent a normal force. I use a lowercase f specifically in the case of friction. I use W to represent a weight. Remember, weight is another word for force due to gravity. Okay. You may ask, why do we use W for weight instead of G for gravity? Well, remember, we've already encountered little g as the acceleration due to gravity and gave it a value of 9.8 meters per second squared. So that's taken. There is also a big G, which is associated again with the force due to gravity, which we won't encounter for a couple of units yet. And it has this value of 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. No, you do not need to memorize that for this unit. So little g is taken, big G is taken, therefore we went with W for weight. And lastly, T for tensions. Okay. There are times when you really think that there should be a force in a particular direction doing a particular thing, but you can't identify the cause of the force. So you can't identify that first subscript. Chances are, if you are in that position where you really want a force, but you can't identify that first subscript, that force does not exist. So let me give you an example. You see a ball come rolling across the floor. Oh, let's not go with a ball. Rolling things get difficult. Let's go with a block. So it's a block sliding across the floor. You didn't see what happened to cause that block to be sliding across the floor. You have no idea how it got to be moving in the first place. What you know is it is moving, let's say in this direction, and it is slowing. So when I think about the forces on the block, I know it's slowing. Well, that's most likely due to friction from the floor on the block. I see that it is being supported by the floor, so I add a normal force between the floor and the block. Well, the block has some mass, so it's got to have some weight. I can't draw the bottom of my arrow there, so imagine it. So you get the weight of the earth on the block because the earth is causing the force due to gravity in this case. And what you really want is you want a force that points in the direction of that velocity. You want a force pointing in the direction of the velocity. But it's not there. That force does not exist. I don't know how to get rid of it. I guess I can just erase it. Let's get rid of it. Oh, I erased my block. Come back, block. There we go. Right? That force does not exist. And a sign that that force does not exist is you couldn't identify that first subscript. Okay. Quick comment. A mass or a measurement of mass is a measurement of the amount of stuff that goes into making up something. And it's a really not scientific sounding definition, but I really haven't seen a lot of better ones, right? mass is in kilograms. Okay. Weight is the force due to gravity acting on that stuff. So weight is a force. It's measured in newtons. And it is the case that these two things are related. If you are near the surface of the earth, the weight of the object will equal the mass of the object multiplied by the acceleration due to gravity. So weight equals mg. If I take an object out into space, its weight will change. Its mass will not. Why does the weight change? Well, because the value of g changes. We'll go into this more in a couple of units, but g does not go to zero, contrary to anything you might think. Okay. In English units, when we stand on a scale, the thing that we measure is a weight in pounds here in the US. If you go to Europe and you stand on a scale, you do not read a weight in newtons. The scale has been calibrated to give you a mass in kilograms. And last slide for this unit, friction. Okay, friction is a force that resists motion. There are a lot of different types of friction. You can think about the friction between a block and the floor. That's a type of friction. You can think about air resistance. That's yet another type of friction. Regardless of the type of friction, friction always points in the direction opposite of the object's velocity or the direction the velocity would be in. So, for example, if I had a ramp and the block was going up the ramp when its velocity, don't ask me why it would be, I don't know, then friction will point down the ramp. If, on the other hand, I look a while later and I now see the block moving down the ramp, so velocity is now down the ramp, then friction will point up the ramp. And maybe yet another later time, I look and I see a different block, a bigger block with more mass. It doesn't look it, but let's say this is a 2 kilogram block, this is a 2 kilogram block, and this is a 20 kilogram block. And I see this one isn't moving. Okay. Why isn't it moving? Well, the friction is too big between the block and the ramp. So what direction does it point? If the friction were smaller, this block would try to slide down the ramp. So the velocity would be down the ramp. Therefore, in this case, the friction would be up the ramp. This concludes this portion of Unit 6. In the next portion of Unit 6, we're going to learn about free body diagrams, which are a method for keeping track of the forces acting on an object.